So what's the definition of the cross product of two sets? Mhm. A comma B for all A and B and B. Mhm. De Morgan's laws. A complement intersected with B complement. Mhm. Or A intersected with B complement is A complement, union B complement, where A and B are sets. So you have to have the let A and B be sets. And then the distributive laws. A intersect with B union C is A intersect with B union A intersect with C. Or A union B intersect with C is A union B intersected with A union C. Or A, B, C, and D are sets. Okay, so that's the quiz. Let me get the projector turned on. This popped up. The computer decided to update about 10 minutes before class started. It started updating. And it just finished about 3 minutes ago. It took it 30 minutes to update. Usually it doesn't take that long. But it did. Okay. Yeah, 2.1 homework is due tonight by 10. Thursday is a review, which means that there's no outline due on Thursday. Homework is due at 10 o'clock Thursday night for 2.2, which we're covering today.
So can you walk this to
No. No. I want us falling behind. Okay, so I suppose I need to be this open first of all. We have a few definitions. Did I give you guys the notes? I did not give you guys the notes yet. Pass it down. So we have a few definitions to cover first of all. Make this so that it fits on. Well, what's our first definition? It says let A and B be sets. The union of A and B is a set of all X. So X is in A or X is in B. The intersection is everything in both of them at the same time. So if you're drawing a picture, remember they mentioned Venn diagrams in the over here. So let's kind of draw a Venn diagram for this. The screen around. So I don't know why it always thinks that it needs to go sideways. Turn back around. Yep. Now it's the right direction. So if you're drawing Venn diagrams, here's our set A, here's our set B. A union B would be all of that area shaded. What would be the intersection? It's not doing it's also doing trend. The projector's having problems. The intersection is going to be, I'll put it in a rectangle. Then U is everything outside. This is A, this is B. There's the intersection. Everything in A or A and B at the same time. It has to be in both A and B. What is the difference? Let's update something else. We're not updating again. Silly computer. So what would A minus B look like? It's everything in A, but not in B. Does that make sense? As far as pictures go? That's our definition. Now, we have another definition. This is when two sets are disjoint. Two sets A and B are disjoint if and only if their intersection is an empty set. So if you were drawing a picture of disjoint sets, would they overlap or not? No. You have to draw them as two separate circles. They can't overlap. When they're disjoint, they don't overlap. And then the complement of a set. This is our set U. Here's our set A. What would be the complement of A? I'm going to draw a set B too. The complement of A is going to be everything outside of A. It can be B, but it just can't include anything in A. This program has a nice feature. If you color something in, it erases it. So we'll do it this way. So the complement is everything outside of A. It can be in B, but it can't be anywhere in A. And then our last definition was our cross product. You know, the cross product used to drive me crazy. Through analysis, I never had a set theory and logic class. They didn't teach it at Southwestern. To my knowledge, I don't think they do yet. But, you know, so whenever I saw sets, I was, what is this cross product thing? It was a very scary beast. It wasn't until graduate school that I figured out it's just our XY plane. It's just your XY plane, X comma Y. That's all it is. So don't let it be too scary. So if you have elements in your set A and elements in your set B and you want to find your cross product, you're just doing the A's, the first ones come from like your x-axis and the second ones come from like your y-axis. That's all it is. It's your XY plane. Okay, so let's look at some examples. As far as a cross product goes, is 3, 7 equal to 7, 3? No, they're two totally different points. So the ordering inside the points matters. Ordering inside a set does not matter. I could write this set A right here as the set 2, 1, 4, 5, 7, and that's the same set. Ordering does not matter for sets. Ordering does matter for the cross product. So keep that in mind. Okay, you guys get to do this. 1, 2, 3, 4. 1, 2, 3, 4. Back row. Pick one each and come up on the board and write them down. A union B, A intersected with B, A minus B, and B minus A. So whoever's on the back row gets to do board work today. That means you have to get up off of your chairs and come forward and write them on the board. Yep. It's called interactive today.
Oh, right, that's, okay. Does it matter what we do?
Bailey chose A union B.
Okay.
So Kalai, you do A intersected with B, and you get A minus B, and you get B minus A. That keeps it in some order of order. Okay, so you guys have to help them out here. That's all right. No, yours is A intersected with B. Intersection is what? Yes, what's in common? So what's in both sets?
Only 2, right?
Yeah,
Oh,
1
wait,
and
right.
5.
Yeah, right. Yeah, I'm doing.
For A minus B, it's what's
What's in A, but not in B.
2 or 7.
2 or 7.
Yeah, 2,
It's
4,
just-
7.
Basically, it's not the best.
Yep, no, that's
Yeah,
definitely
essentially.
Interesting.
Okay, so do we believe everybody? again on the second row. Oh, I'm in the right.
It's 2, 4, and 7.
Oh. 2, 4.
It's okay, mine like
Yeah.
decreases.
I started writing
and it's
3
less
for some
upwards.
reason. 2, 4, and it's 7.
Yeah, so how do you get B
Those are
minus A?
It's not.
Ish.
It's the ones that exist in A but not in B.
Yeah,
I
the
got
ones that are in A but not in B. Can we do that on our homework? We have a homework problem like that.
Yes.
Yay, an easy one.
Can we do it? Yes, we can. Sorry.
Yes, we can.
That's literally what I thought.
So let me write this down here so that we have it for posterity.
That was a long time ago. Oh my goodness.
You guys have probably done tutoring for survey and have done this. So you have one, we need a 3 and a 9. I know, you put it in order and I did it. A intersected with B is everything that they have in common. What's that? 1 and 5. A minus B. What'd you get for A minus B? 2, 4, 7.
Three and 9.
Oh, 3 and 9. There we go.
It's like Q.
It's like what, huh?
Q.
U?
Q.
Oh, Q. Yeah, it does look like a Q. Let's fix it. I'm not sure that's much better.
It's like A.
It'll live. Okay, so that's our example there. I think that's all that's on that page. We have a couple more examples. Next row, that would be you guys of row 3. You're going to do number 7. So you have to find A union B, A intersected with B, A minus B, and B minus A. But now you have intervals instead of
Oh, us
discrete
again?
sets. No,
Oh.
second
I was gonna say both B. No.
row. No, row 2. You guys already agreed. So you guys all pick one, and then I'll be the last one that you guys don't pick. You're gonna do that one.
Okay.
Yes.
So it looks like
I'll
a
just
B
do the
minus
one
A.
that was.
Yeah, and I have A minus B.
Okay.
So let's see, what is A?
So, 4 to 8. So 4, 5, 6, 7.
No, you 7.
It's not 7 and 8. And then it's 8, 3, 3, 6, 3, 6. So 4, 4.
So draw yourself a number line, you'll be able to see what
4,
you're
5, 6, 7. Oh.
Yeah, draw a number line, then you'll see what you're doing.
So 1, 3, 4, 5. This is 4, 5, 6, 7. So the only one is 7.
So if we,
Yeah. No, and 4 is in.
oh yeah,
So it's only.
On your number line though, remember everything in between lives on it?
so you,
So if you go from
6 parentheses of 7.
3 to
Oh.
6 is A, right?
Yeah.
And then B goes from
You have to write it in the.
to 8.
yeah,
So if you're doing B minus A, then you're taking away this right here, so you're gonna have a parentheses from 6 to 8. Which is what you were getting your 7 from. But we have to write it as a parentheses because it includes everything in between. So this isn't the point, actually including 8. Oh, mhm. Yeah. Does that make sense to everybody? You just draw your number line. So I'll put the number line on here. So we have from 3 to 6, and that's A. And then at 4 to 8 is B. And so then B minus A is going to be starting here at the 6 and going to the 8. But 6 is included in what's removed, so it's parentheses 6 to 8. Does that make sense? Mm-hmm. So then what would A minus B be?
3 bracket 5.
How about to 6?
So, well, whoever did A minus B said
I did put 5.
wrong.
Oh, yay. How about the 6?
Can we get a free plan?
How about a cookie?
Okay.
Okay.
Don't have any. You have to bring them next time.
You need to bring them.
Do what, huh?
No, this is,
Cookies.
I know better than one, so that you can feel.
I have to make them first. Okay, so then what would A union B be? Yeah, it's everything. And A intersected with B?
Bracket
4 to 6. Yep.
Oh, yeah.
There we go. Make a 46.
I was dressed.
Now, look at this example. This is 4 to 8 minus 5 to 6. So here's 4.
Oh,
Here's 8. And then over here is going to be our 5. So this is the first one. Yeah, so it's going to be 4 to 5. And is it bracket or parentheses on the 5?
Bracket.
Bracket, because it was a parentheses. And then it starts at 6. Is it bracket or parentheses? Parentheses. And 8 parentheses. Can we do that? Looks like it. You just did. That's correct. I think you did. Okay, give an example of two disjoint sets.
1, 3, 4. Oh, that was fun.
You guys think alike. That would work. A whole bunch of zeros.
I mean, that's really what I would choose.
can we get a one?
Now let's calculate this. A cross B. So this is going to be 1 from A with 2 from B, 1 from A with 3, and 1 to 4. And then it goes 2 with each of them. It's more fun that way. Tell me about B cross A.
So 2, 1, 3, 1, 4, 1.
Mm-hmm.
Basically,
Yep. Are they the same sets?
they're not.
No.
No, they're not the same.
One similar type.
What that tells you is that order matters for those guys.
Yes,
Mm-hmm. Don't get them confused. I think that's the last one. Yeah,
we're friends and he's
no, there weren't.
Right?
Now we have theorems, and they proved. We're just gonna prove yeah, all of them, right? No, we're gonna prove M on this one. That's the one I wanted to look at. So what does M say? I scrolled past it. This is a distributive. Yeah, intersection over union. So that's the one we're going to actually prove. So when you're proving, notice that this first part right up here, this is a set. This second part is a set. How do you show that two sets are equal? That would be writing them as equal, not showing them as equal.
You find an object.
You have to start with you have to show set containment going both directions. So you have to show the first is a subset of the second. The second is a subset of the first. You have to show set containment. That's how you show equality of sets. So if we're actually going to do this one, let's go. I like to type the proof stuff. This is going to be the proof for part M. So what's the hypothesis? let A, B, and C be sets,
Yeah,
right?
like A, B, and C
Yeah.
sets. And then,
And then to go the first direction,
let A intersect B.
how about we need something in it, right? And B union C. If X is in A intersected with B union C, then where does X live?
And there's in A
Yeah.
and B or A.
By the definition of an intersection, X is in A and X is in B union C.
I think we're going to
Do what, huh?
go.
Up here?
Oh,
That's so that which way I'm going on my set containment. I'm starting with the first step, going to the second, and then when I go the other direction, I'll put the other arrow. That's just for my sanity. Yeah.
And then by definition of union. Oh,
X is either B or C.
Yeah.
X is in A and B or A.
Well, I'm gonna do,
And then.
and I'm gonna put parentheses around this. Yes, because then I'm gonna apply a property that we learned from logic. And that is if we have P and Q or R, you know that that is equivalent to P and Q, or P and R. So now we're gonna have X is in A and X is in B, or I need to put parentheses around this. X is in A. Then what do we do? I'm gonna do them both at the same time. So then that means X is in A and B. Oh, I guess I won't do them both at the same time. X is in A intersected with C. And then we have X has to be in A intersected with B, union, because of the or, A intersected with C. Now, as desired is just meaning that's where you were trying to get to. So if we go back up and look at M right here, that's where we were trying to get. So that simply means I got to what I wanted to get to. Now, we're going to go back the other direction. And I always forget how to get that arrow, so I just go get it. To go back this direction, what's the hypothesis? What do we let X be an element of? The thing we just had. What does that tell you then? Yes, I am. We could. By definition of intersection.
Going in direction and literally like the same exact steps.
Pretty much the same exact steps. So you're using our statement right here. We can now go back to this one. X element of A and X is an element of B or C. Is that the one I just had? Then you go up one. Oh, whatever you want, but you have to have something to start each sentence. You can't start sentences with variables. It does.
I know, right? That's an F,
The app thing.
because like this entire top line, you're like,
Let me see what she-
Mm-hmm. Try putting a derivative symbol after an F. It becomes part of the F and you can't see it unless you compile it. Then you can see it. But when it's just like this, it doesn't.
You have to have
And so let's go get what we're trying to prove. So we have set containment going this direction. And we have set containment going the other direction where it said as desired. So I'll put this set containment going the right direction over here. What does it mean when you have set containment going both directions? It's equal. We can put our equal sign. So to show equality of sets, you have to show set containment going both directions. That's what we have to do. So that's one of them from that list. Let's look at the next list of theorems here. I forget which one I wanted to prove next. I didn't want to go that far. C and G. Those are the parts we want to prove on this one. Those ones are actually shorter. What's the hypothesis? Let U be the universe and A and B be subsets of U. You gotta get it all. And then what comes next? If we're proving part C, we want to show A intersected with A complement is an empty set. So to show set equality, we have to show set containment. So let's start with the first side and get something in our A intersected with A complement. Does that make sense? Well, if A is in A intersected with A complement, if X is in the intersection of them, then that says X is in A and X is in A complement, right? Intersection would be and, right?
Right.
Okay. But what does that tell us then? That means X is in A and X is not in A. No, it just means that X has to be, X is not equal to itself.
Right, so we know that.
Yes. Yes, it
Yeah.
is.
X is not equal to itself, therefore.
Well, it can't be equal to itself if it's in both sets.
Right.
Mhm.
It's just so weird to say.
It is. It's a
Not
very
equal to
weird
itself.
thing to say. So thus, it's the same thing as saying x isn't equal to x. And if I get you to think x is not equal to x, I can get you to jump to the definition of an empty set. Because of the definition the book uses. But yeah, you could word it the other way. But I chose to word it that way because of our definition for an empty set. Mhm. Is a subset of empty set, not equals empty set. Now, what do we know about the empty set? It's contained in every set out there, right?
Uh-huh. Okay.
So it's contained in, well, I need to know it's in A, and I need to know that it's in EMPTY. Empty set is contained in a complement. So we have a theorem statement that says something about if it's contained in two sets and is contained in the intersection of both sets, right? I don't remember what theorem number it is. I'll just write it down. If it's in both sets, it has to be in the intersection of both sets. I have set containment going both directions. What's our conclusion? Set containment goes both directions has to be equal. Question.
Is there a difference between the symbol you have for the subset and then the symbol that's up there next to intersect?
Which symbol?
On that toolbar on top.
Oh, on which one?
The one right there.
This one?
It says
Yeah,
subset.
this one is just a strict subset.
Okay.
So it's a proper subset.
And then what's the other?
And this one is a subset or the same set.
Oh, okay.
So you're allowing the set itself to be part of it. The other one, that means that it's a proper subset. It misses something from the original set.
Therefore, we're not able to do this. Right?
Yeah, it won't be
It's
able to
just like
equal to
the-
itself.
Be less than or equal to.
That's
sign,
exactly it.
But with subset.
But with subset. Oh, no, just as long as you don't do it again. Yeah. Okay, so that's part C. What was the other one I wanted to do? Let me look at my notes. Part C and part G. What's the hypothesis for part G? Yeah, but we have to show set containment again, and it's A intersect with B complement. This would be De Morgan's laws. So we're going to have, not a capital let X be in A intersected with B complement. What does it mean then if X is in A intersected with B complement? That means X is not in A intersected with B, right? Outside of A intersected with B. But if X is not in A intersected with B, then what do we know? Well, that's where we came from. Yeah. If you think about drawing yourself a picture, it's not in the intersection of A and B. I know it's not here. So that means it could be out here, it could be here, it could be here, and it could be here. All of those, these three right here are represented by not A. And these three right here are represented by not B. So that's why we say it's not in A or it's not in B. Do you guys see that visually? That comes from that visualization. So then that says X is not in A. X is not, no, I didn't do that, not in B. But if X is not in A, then what does that tell you X lives? A complement, right?
That's capital C.
Yeah, I'm using capital C for complement.
Doesn't matter what it is.
No, just looks better to me if it's capital. Doesn't matter at all. So this is A complement intersected with B complement, right? Therefore, since X is arbitrary, I know that I know that A intersected with B complement is contained in A complement intersected with B complement. Go back the other direction, what do we need to do? Can we write this one if and only if? If you start at this line, you get to this line, you get to that line, so that goes to that line. So this would be if and only if, right? So let's just go ahead and make it if and only if. That shortens our proof. I could have done that earlier, but I wanted to show you both directions. So right here, oh, we need an if and only if right here. I better put that up on different lines. Okay, so X element of A intersect with B complement if and only if X is an element of A intersected with B. And I get an equal sign right here. And then right here, I'm going to just do this. Instead of writing the hypothesis separate up here, it's included on the first line in our box, in our centered box. So that's an if and only if proof. You can do if and only if proofs. As long as you check to make sure that they work, you can do if and only if proofs in Normal. Did you guys have any questions on this theorem of the cross product proofs? This one? Because when you do A cross C, A union with C, then that C, right here you have A cross B, so all the A's are paired with B's, all the C's are paired with D's. But when you put the A's and C's together and pair them with the B's and D's, you get these C's paired with those B's and these D's paired with those A's. So you get something extra. That's why you have the extra. Because here it's just A's are paired with B's, but when you put the C's with it, then the C's will go with the B's too. Yeah. That makes sense? Try this one on the homework. I want to make sure you guys can do the homework on this one. So let me tell you, I don't remember the homework problem number, but it's, I think it's number 16 on your homework. I think it's the last homework problem. So go ahead and start on the homework, but do number 16 on the homework so that we can make sure we know how to do the cross products. 16, is it 4? I know you have one with cross. It's going to be 14.
14 is proof that A cross C.
If and only if A equals to B. Mhm. Yeah, so yeah, do number 14.